Hi everybody, this video will go over section 2 of chapter 8 and we are going to talk about the student's t-distribution. Specifically in this chapter we're going to talk about its purpose, what its properties are, and how to find what we will now call t-values, not z-values, but t-values, given the area to the right of t, given the area to the left of t, or given the area between negative t and t. Okay, the t-distribution was developed by this gentleman named William Seeley Gossett in 1876. Now you might think that he developed it at some university or at some think tank or some research institute. Nope, he developed it at a brewery, namely Guinness Brewing Company in Ireland. What he was interested in was working on problems where we actually had small sample sizes. Now, for example, 3 or 4 samples of Bailey, 3 or 4 samples of hops, stuff like that. And once he came up with his result, he wanted to publish it. However, Guinness did not want their name associated with the publication, and they did not want him to use his real name in the publication because that would map it back to Guinness. For some crazy reason, they wanted to play no part in this. I don't understand why. That must just have been the business mentality at the time. So he published it using a pseudonym. You guessed it, student. Okay, so what is this distribution all about? Well, it is a probability distribution, just like the Gaussian distribution. As a consequence, the area under the curve, the area under each of these curves is going to be equal to 1. Okay, it's going to be symmetric about the mean, and since this is a standard curve, it's going to be symmetric about the origin, so this side looks just like that. And you will compute the probabilities by computing not the value on the curve, but the area under the curve. Now, how does this relate to a standard normal distribution? Well, if you take a look at this curve right here, this curve right here is the t-distribution when you actually have 1 degree of freedom. And the one thing I guess I should have mentioned beforehand is that whereas the standard normal curve uses mean and standard deviation, or in this case mean is set to 0, in a in its t-distribution we use degrees of freedom. And for 1 degree of freedom you have a curve that looks like this. Now what you'll notice here is that the curve is not nearly as high in the center. It is still symmetric. And the tails are fatter than the tails of a Gaussian distribution. Now as you increase the degrees of freedom, so for example here's the curve for 3, it gets a little taller, okay, and the tails get a little smaller, but still fatter than a normal distribution. As the degrees of freedom continue to increase, 4, 5, 6, 7, you will get closer and closer to the Gaussian distribution. And by the time you get to 30 degrees of freedom, you can barely tell the difference between the curve. Okay, so the student's t-distribution will approach the Gaussian distribution as the degrees of freedom begin to increase. Now, when are we going to use this? Well, we will use this to compute margins of error whenever the population is normally distributed, or, not and, but or when the sample size is sufficiently large. So if you have a small sample, so if your sample size is small, if n is small, but you know the population is normally distributed, you can use the student's t-distribution. You cannot use the Gaussian distribution, but you can, or the normal distribution, but you can use the t-distribution. And if the sample size is very, very large, you can use student's t-distribution. It turns out in our case, we are going to be looking at situations where we have a small sample size, but the population is normally distributed. That's what we're going to be playing with. And that's what we're going to be looking for to decide if we are going to use a t-distribution or a normal distribution. But once again, the properties, they are symmetric about the y-axis. I should have a graph here, but you saw that graph already. It is bell-shaped, just like the other just like the standard normal. It is completely defined by its numbers of degrees of freedom. Okay, once again, the total area under the curve is equal to 1, and the x-axis is a horizontal asymptote. What does that mean? It means the curve will approach the x-axis. Well, let me show you here. The curve will approach the x-axis, but will never touch the x-axis. Okay, as we mentioned before, we will use the t-distribution to actually compute probabilities. And once again, just like the standard distribution, the probabilities are going to be equal to the area under the curve. Sorry, that's not all that vertical. And the way that we compute, the way we find those areas are going to be by looking at t-distribution tables. Now, and this is an example of the t-distribution table that you find in Hawks. Now, the column headers right here, these denote the areas. So that when we're looking for t-values, we're only going to be concerned with the areas of 0.1, 0.05, 0.025, 0.01, or 0.005. The degrees of freedom will be right here. They will be the row headers. And of course, the t-values in this particular case will be in the interior. Okay. The other thing about this is that the tables basically assume that they are given the area to the right of the t-values, which is kind of bizarre because remember when we did the standard normal, the values assume the area to the left of the t-values, or the z-values in that case. Here it's the area to the right. It gets even worse because you can use your calculator to compute these things, and even in the calculator, they assume area to the left. And let's go ahead and work that out using an example. For the rest of this video, we're going to go through 3 examples. This happens to be the first one. Now here, we want to consider the value of t such that 0.1 of the area under the curve is to the right of t. And we want to select the graph which best represents that particular function. Now the shaded area, the shaded part under the curve is the area that we're concerned about. And we are concerned about the area to the right of t. Here's t. This is the right. This is the one that we want. This one right here has the area to the right and to the left. Not that one. You should, and as a matter of fact, in any homework or test, you should never ever choose that one. This right here is the area in the middle. Can't be that one. This one right here is the area to the left. Can't be that one as well. This is the one that you're looking for. Okay, now that we have that worked out, now we want to find that value of t such that 0.1 of the area is to the right of t, and we want to assume that we have 15 degrees of freedom. Okay, so using our tables, we want to go to 0.1 because that is our area. Okay, and we want to go down to 15 degrees of freedom. Okay, that's right here. And that, of course, will lead us to that particular value right there, and that will be our answer for this particular case. Now, you can also do this using your calculator. And here's my calculator right here. Now, how would you do that? To do this, what you need to do is you need to use this thing called inverse t. Great, where do you find it? You will find that in distribution. So you would go second, VARS, and we're looking for inverse t, which is this value right here. So you could either bring it down to inverse t, or you can hit number 4. It doesn't particularly matter. All right, the area, that happened to be 0.1. Okay, the degrees of freedom, 15. Hit enter. Hit enter again. Hit enter again. And notice here we got a value of negative 1.3406. Now that is because the inverse t function in your calculator assumes that you're looking at the area to the left of t. Okay? But you want the area to the right. What is the difference between the two? Well, since the t distribution is symmetric about the origin, that just means we want to get rid of the minus sign. So if we're computing the area to the right, Or if we're using this and we want the area to the right, we take this value, get rid of the minus sign, and you are good to go. And that will give us 0.1341 after we round, which is exactly what we got when we used the tables. All right, let's take a look at our second example. This is to find the t-value for the area to the left. And here we want to find the t-value such that 0.05 of the area under the curve is to the left, and we want to select the graph which best represents the description of t. And once again, you'll get the exact same 4 options we had before. I didn't feel the need to repeat that. Obviously, you want to pick the option where the left is shaded and only the left is shaded. And then that brings us to part number 2. All right, now, once again, we are going to assume that the degrees of freedom here are equal to 8 and find the correct t-value. Okay, area under the curve is 0.05. That means we are looking here. Degrees of freedom is 8. That means we look here. And that gives us 0.1860. Okay, but remember, the table's interior gives you the value of t, assuming that we're looking at the area to the right. We want the area to the left. Okay, if the t-value is associated with the area to the right of it being 0.05 is 1.860, then the t-value associated with the area to the left being the same is going to be the negative of that, namely negative 1.86. And that is what our answer is going to be. Okay, what about if we're using our calculator? It is the exact same approach. You can go second VARS, inverse t. You can just do that by hitting 4. Now remember, our area is 0.05. The degrees of freedom happen to be 8. And this one basically operates on these, basically uses the area to the left of t. So that is going to give us what we expect, namely negative 1.859, or in this case, negative 1.86. Big thing to keep in mind here is that if we're looking, if area to the right implies a positive value for t, at least in this particular course, area to the left implies a negative value for t. So if the area is to the left, t should be negative. If the area is to the right, t should be positive. What about our last case? Here, we want to consider the value of t greater than 0, such that the area under the curve between negative t and t is 0.9. Okay, well, namely, we are looking for this particular graph. So this is the one that we want to select. All the other ones are going to be wrong. Okay? Now, to actually figure this out, what we need to do is we need to figure out the area under one of these tails. Okay? Because remember, our lookup table, basically, and for our table lookups, we are given this particular area, and it finds t for us. So this area, we cannot use this area directly. We have to use this area to actually compute what the area is here or there. Okay? Now, remember, the area under the entire curve is equal to 1. Okay, so if the area in the center is equal to 0.9, then the area in both of the tails is going to be 0.1. Okay? And once again, since this is symmetric about the origin, half of that area is going to be in one tail, the other half is going to be in the other tail. So the area in exactly one of those tails is going to be 0.05. So the area here is 0.05. The area here is 0.05. Okay? So now that we have that, we can go to our tables. We want 0.05. It's right here. All right? We have 60 degrees of freedom. There's 6. And that is the t-value we're looking for. Now, and since we're looking for the positive value of t, that happens to be our answer. Okay? And once again, 0.05 is there. We want the value to the right. That is going to be 1.943, and there we go. Now, what about using your calculator? All right, well, to do that, we can once again go into inverse t. That will be second VARS, number 4 for inverse t. The area is 0.05. The degrees of freedom is 6. And since this basically is finding the value of t where given that the area to the left is 0.05, it's going to produce for us a negative value. But we don't want the negative value, we want the positive value. So even though we get a negative number, since we're looking for the area, since we are given the area in the middle and they want the positive value of t, we just want to get rid of the minus sign, which will give us which will give us positive 1.943. And that is all that I have for this particular video. Stay tuned for the last video in this section where, yeah, you guessed it, I'll do your homework. And until then, this is Bob Boyle, signing off.